we will talk about the chemistry of life, chemical level of organization. You know from last lecture that there are different levels of organization from the smallest to the largest, right? Smallest is the chemical level. And the chemical level includes atoms and molecules, right? So today we will talk mostly about the atoms. First, we will talk about the element, atom, subatomic particles, isotope, radioisotope. What are those things? Remember, all those are microscopic structures. Then we'll talk about the chemical bonds that attract the atoms or molecules, bind the atoms or molecules. Those are the bonds. There are different types of chemical bonds. We'll see the important chemical bonds, what in our body. Then we'll talk about the chemical reactions. You know, inside the human body, many chemical reactions occur, right? But we can classify or group those reactions into different types of reactions. So we'll see important types of chemical reactions that occur in the body. Then we'll talk about the organic and inorganic compounds. In our body, we have both organic and inorganic compounds. So we'll see the important organic compounds and inorganic compounds that are present in the human body. Okay? Then we'll talk about the most important and abundant chemical in our body, which is the water. So we'll talk about the properties of water. Then we'll talk about acids and bases. Then we'll talk about, these are inorganic compounds, by the way, water, acids, bases, those are inorganic. Organic compounds include proteins, carbohydrates, fats. These are organic compounds. So we'll talk about both inorganic and organic compounds. Then we'll talk about the source of energy, how we get energy. First, to know the atom, you need to know a matter and an element. So if you see from the smallest, first atoms, then elements, then matter, and matters can be present in three forms. Okay, solid matters, liquid matters, and gases or gaseous. So the matters exist in three forms in nature. Now we can say that atoms are the building blocks of elements. So atoms join together to form elements, and elements are the building blocks for the matters. Okay. Okay, so that's how the matter is composed of. Atoms form elements, elements form matter. Now, if you see an atom under a very powerful electron microscope, you will see inside the atom you have subatomic components. Subatomic components. What are the subatomic components? Electrons, protons, neutrons. Okay, so we have electrons, protons, and neutrons. So those are called the subatomic particles inside the atom. You will find them. Okay. Elements cannot be split into simpler substances by ordinary chemical reactions. It's difficult to break an element by ordinary chemical reaction. But you can break it and see that elements are formed by the atoms. And elements are designated by chemical symbols. How? If you indicate an element using two letters, for example calcium, first letter will be capital upper block and second one will be lowercase. Okay. Similarly, sodium, Na, first one is upper case, second one is lowercase. If you use only one to indicate an element, for example nitrogen or carbon, we use capital, okay, uppercase. So that's how the elements are designated, the symbols of elements. Only 92 elements have been discovered in nature until today. And all the matters you see, in this room even, you will see more than 92 matters, right? So how thousands of matters are formed? By combining two or more elements, okay? So you combine two or more elements to create a matter. Make sense? So that's how you see so many matters and in three forms: solid, liquid, and gaseous. Now, since we are learning about the human body, we need to know which elements are important or mostly present in the human body. Four elements form about 96% of human body mass. What are those four elements? Carbon, hydrogen, oxygen, and nitrogen. You need to know this. Four. They form about 96% of the human body mass. Other elements are present in a small amount, for example, but those are also very important. Although they are present in very small trace amount, they are very important. What are other important elements in human body? Calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, and iron. Just let me give you a couple of examples. Although these are present in very small amount, they are very important. For example, if the calcium concentration in your blood gets lower, that is called hypocalcemia. Hypo means low, you know, right? Hypocalcemia. In that case, your muscles will be paralyzed. Respiratory muscles will not work, so you won't be able to breathe. The person may die. So you see, very important, although they are present in smaller amount. Iron. Lack of iron causes anemia. Okay, iron deficiency anemia, we use that term. Okay, so those are also important elements. Now, if you see the structure of an atom, as I have mentioned, inside the atom you have subatomic particles or components. What are the subatomic components or particles? Electrons, protons, neutrons. So we'll see their locations, where they are located inside the atom. Okay. So if you see a structure of an atom, it has a nucleus and a shell. The outer layer is called the shell, and in the center you have the nucleus. In the nucleus, you have two subatomic particles, protons and neutrons. They are located in the nucleus. So in the nucleus of an atom, if you have, for example, 4 protons, you should have same number of neutrons, equal number of protons and neutrons in the nucleus. Okay. For example, this is an atom, it has 4 protons, it must have same number of neutrons. Protons carry positive charge. That means protons are positively charged particles. Okay. Neutrons are neutral. They don't carry any electrical charge. That's why neutral. Okay. So now we can say that in the nucleus here you have how many positive? 1, 2, 3, 4. This nucleus has 4 positive. Electrons are present in the shell. So these are electrons. And electrons carry negative charge, minus. And in an atom, you have equal number of positive and negative. Okay? Electrons are negatively charged particles. So now you see you have electrons on the shell, protons in the nucleus, and nucleus has 4 plus, and on the shell you have 4 minus. So equal number of positive and negative charges. Is it clear? So what should be the status of this atom? Neutral. Makes sense? Because equal number of positive and negative makes the atom neutral. So atoms are neutral. Is it clear? So we can say atoms are neutral. Electrons continuously orbit the nucleus and circles the nucleus, moves. Okay, electron moves very fast around the nucleus. Protons and neutrons are static, sit in the nucleus. Okay. Now, the weight of a proton and neutron is equal to, so one proton or one neutron equal to 1 atomic mass unit. Okay, so atomic mass unit is the unit of measurement of the weight of protons and neutrons. Electrons are weightless. We consider electrons as weightless. The reason is the weight of electron is so negligible. that we cannot measure. Okay, so we consider that only protons and neutrons have weight, electrons are weightless. Now, the two terms we often use, one is atomic mass number and another is atomic mass number equals to the protons and neutrons. So if you add the protons and neutrons, you get the atomic mass number. So what is the atomic mass number of this atom? 4 plus 4, 8 atomic mass unit. Makes sense? 8 atomic mass unit or dalton. That's the unit. Because 4 protons and 4 neutrons. We don't include electrons because they are weightless. Atomic number is different. Atomic number is the number of protons only. Okay, so the atomic number of this atom is 4. That's the number. Okay, we don't use the unit. So we need to know the atomic mass number is double than the atomic number. Okay, so atomic number of this atom is 4 because it has 4 protons. Now, we know that atoms are neutral. Sometimes what can happen, the number of neutrons can be changed, can be different than the number of protons. For example, this one has 4 protons and here you have, for example, 3 neutrons. So unequal number, right? Because of the change of the number of neutrons. If that happens, this atom is now called an isotope. So this atom is now called as an isotope if the number of neutrons changes. So now no more protons and neutrons are equal. Is it clear? Make sense? Did you get it? So if in the nucleus of an atom the number of neutron is different than the number of proton, in that case that atom is considered as an isotope. Is it clear? So now you tell me, what's the atomic mass of this isotope? Atomic mass number 7. 4 plus 3, right? It is less neutron. So atomic mass number of an isotope is different than the atomic mass number of an atom. Okay. Now, isotopes are not harmful, but sometimes what can happen, due to that unequal number of protons and neutrons in the nucleus, an unrest, instability can be created in the nucleus because the balance is lost. Make sense? The number is different now, so the balance is lost. So that can release radiation. If that happens, most of the time isotopes will not release radiation, but sometimes because of that unequal number the nucleus can release radiation. In that case this isotope will be termed as radioisotope. You hear that term, right? Isotope, radioisotope. Radioisotopes could be very harmful, extremely harmful, can kill the tissue cells, the radiation, right? But good thing is that we now know how to use the radiation for good purposes. For example, radiation is used in X-ray because radiation can pass through the soft tissue, right? So you can take the picture from deeper part of the body. Radiation is used. We know that radiations can kill the healthy cells, right? By human cells. But now we can use the radiation to kill the cancer cells. Can particularly, specifically, we can put radiation on bad tissue or cells and kill them, right? So to treat the cancer. Radiation is also used to preserve the food. So those are the good uses of radiation. Okay, so you have learned about the atoms, isotopes, radioisotopes, right? Here you see an atom of helium. It has two protons, two neutrons in the nucleus and two electrons on the shell. All atoms have protons and neutrons in the nucleus. Only one exception is the hydrogen. Hydrogen atom doesn't have any neutron. Okay, so this is only exception. Okay, now in an atom there could be more than one shell. So for example, this is the shell, but it can have more than one shell. So this one has 3 atomic shells, and the outermost shell is called the valence shell. So valence shell is the outermost shell of an atom if the atom has more than one shell. Okay.
The other ones have names too, or just the outside?
Just the outside is called the valence. Others are number 1, number 2 shell. Okay, from inside to outside. Okay. Now we'll talk about the chemical reactions. Before we talk about the chemical reactions, we'll see what is an ion. So again, this is an atom. It has, for example, 3 protons. It must have 3 neutrons and 3 electrons because it is neutral. Okay. These are negative charge, 3 negative, protons are positive, we know that, so 3 positive here, it is neutral. Now there is another atom here, it has 4 protons, 4 neutrons and 4 electrons. So this is neutral, another atom. 4 minus, 4 plus. Now, if these 2 atoms come close, what can happen? An electron can be transferred from the valence shell to the next, from the shell of one to the next. Now, if this electron leaves this atom and it goes to that atom, now you tell me, how many negative here? Everybody. How many? 2. How many positive? 3. So, is it neutral anymore? So, it will get what kind of charge? Positive or negative? Positive. Are you positive? Why? It will become positive because it has 3 positive, 2 negative, right? 1 more positive. So this will become what? Positively charged atom. Is it clear? Now you tell me what will happen to this one. This one has gained 1 negative, right? So it has how many negative? 1, 2, 3, 4, 5. How many positive? 4. Is it clear? So 1 negative is more, right? So it will become what? Negatively charged. Is it clear? So it will become negatively charged atom. When an atom gains electrical charge, it is called an ion. So these atoms are now what? Ion. Because they have gained electrical charge. This one is positively charged ion. This one is negatively charged ion. Is it clear? And positively charged ions are called cation. Okay, and negatively charged ions are called anion. Okay, so cation and anion, positive and negative. Now you tell me, if one atom is positive, another is negative, what will happen between them? Something will be created between positive and negative, right? Attraction, bond. Is it clear? Positive and negative, they will attract each other. We know that, right? So that bond is called the ionic bond, the attraction or ionic bond. So ionic bond is formed by giving and accepting the electrons. By giving electron, atom becomes what? Positive or negative? You tell me. By giving electron, atom becomes what? Positive. And by receiving electron, ion becomes negative. Is it clear? Okay. And they attract each other. This is called the ionic bond formation, right? And the process that donating and accepting and formation of ions, that process is called ionization. So ionization is this process, okay? And bond or attraction is the ionic bond. The ionic bonds and covalent bonds and hydrogen. Among these three, these are common types of bonds that attract the atoms in human body. Now, among these three, the most common is the covalent bond. Most common is the covalent bond. And ionic bonds are medium strength bond that I have shown you. This is the ionic bond, medium strength bond. Covalents are most common and most strongest bonds, okay? And then hydrogen bonds. Hydrogen bonds are weak bonds among these three, weakest. And hydrogen bond in our body, hydrogen bonds hold the water molecules together. So water molecules are held together by the hydrogen bonds. For example, this is, you know that water is H2O, the two hydrogen, one oxygen. This is the water molecule, H2O. This is another water molecule, okay, H2O. Now, in a water molecule, oxygen is negative, weakly negative, and hydrogen is weakly positive. So this is weakly negative, these are weakly positive. So what happens when water molecules come close to each other? The weak positive and weak negative attract each other. So this is hydrogen bond. It's created by the attraction between the weakly positively charged hydrogen and weakly negatively charged oxygen of water molecules. Okay, and these are weak bonds. Covalent bonds are very strong and they are formed by sharing the electrons between the atoms. For example, this is an atom, these are the electrons on the shell, and you have one electron here, and this is another atom, you have electrons here, one electron is here. Now you see these two electrons are directly attached to each other, no gap, and they are shared, we say, by both. So we consider these two as a part of this, also as a part of this. So when that is called sharing of electrons. Okay. So this is the covalent bond. By sharing of the electrons, covalent bonds are formed. Okay. Covalent bonds are formed by sharing the electrons. So those are three important types of bonds that hold the molecules or atoms in our body together. We have talked about cations, anions, positively charged, negatively charged. Okay, this is something interesting conversation between two atoms. They're talking to each other. The first one is saying, damn, I lost an electron. Second one is asking, are you sure? First one said, I am positive. So you know that by losing an electron, an atom becomes what? Positive. That is called cation. And by gaining an electron, an atom becomes negative. That is called an anion. And they attract each other. That is the ionic bond. And that process is the ionization. Now you will understand here. I have already shown you. You see in the left side, sodium and chlorine. So one electron leaves sodium. So in the right side, you see sodium becomes positive because electron has left, and the one has gained that electron, that is the negative, and they will attract each other to produce sodium chloride. Here you see three pairs of electrons have been shared. So that is the covalent bond, sharing of the electrons. I have shown you here. Water molecule, weakly charged, negatively charged oxygen and weakly positively charged hydrogen. They attract each other, and that is the hydrogen bond. How you know that water molecules are attracted to each other? They stay together. How you know that? Sometimes you'll see small flies can walk on the water surface, right? Because the water molecules are together. So that creates the surface tension on the surface. Another easy way, if you dip your finger in water and bring it out, you'll see water molecules, all molecules try to stay together, right, to form a ball. Then when they leave, they also drop as a ball, right? Not like water molecules are getting separate from each other. Make sense? So water molecules always try to stay together because they are attracted by the hydrogen bond. Okay. Now, as I have mentioned, that thousands of chemical reactions take place in our body, many. We can group those chemical reactions into three types. We can divide them into three types of chemical reactions: synthesis reactions, decomposition reactions, and exchange reactions. Synthesis reactions create larger and complex molecule from smaller simple molecules. So smaller simple molecules get together, join together to form a large complex molecule. That is the synthesis reaction. For example, if you drink a lot of glucose, sugar, too much, then what will happen? Glucose molecules are very simple. Most simple carbohydrate molecules are glucose. Okay, so these are glucose molecules, very small and simple. Carbohydrate molecules, okay, small, simple carbohydrate molecules are glucose. We all know that. If you take too much glucose, what will happen? These glucose molecules inside your body will get together to form a larger complex molecule that is called a glycogen. So you see, simple glucose molecules form larger complex molecules, and it will be stored in your body for future use. If you need glucose, for example, when you are starving, your body needs glucose you are not getting from outside, the glycogen will be used to produce glucose. Okay. So you see, this process is called the synthesis reaction. Okay. From simple to complex, larger, small to larger. And synthesis reactions are mainly used to store the molecules in our body. Another example, what happens in proteins? Amino acids are the simplest protein molecules. Amino, you have heard this name, amino acids. So when the protein is stored or is formed, these amino acid molecules, they join together like this by peptide bonds. So amino acids, these are amino acids, right? They join or link together by peptide bonds and form protein. So protein is nothing but amino acid chain of amino acid. So you see, now this is one large molecule of protein. These are small amino acid molecules. So small amino acid molecules join together to form a large protein molecule. That is another example of synthesis reaction. Okay. Now, decomposition is just opposite of synthesis, from large compound molecule to a small simple molecule. Now, as I have already mentioned, if you are starving, your body needs glucose, but you are not getting from outside. So what will happen? This glycogen breakdown will occur. Breakdown of glycogen will occur to release the glucose, and your body will then use the glucose for metabolism. Same thing will happen if your body needs amino acid. Peptide bonds will be broken, amino acids will be released. So from large to simple to small, from large to simple to small, and that is decomposition. We often use the term decomposition. You know that. For example, we say after death, human body is decomposed, right? Breakdown. Exchange reactions. Its name is telling you in exchange reactions, two molecules exchange their parts between each other. Two molecules exchange their parts between each other. For example, sodium chloride and water. Okay. So what happens? The sodium, here you have two hydrogen, so hydrogen, hydrogen, oxygen, this one. So what will happen? The sodium and OH, they will join together to form sodium hydroxide, and this one and this one, these will join together to form hydrochloric acid, HCl. So you see, they have exchanged their parts, make sense, to create new molecules. So new molecules are created. Now this one has parts from both of these, this one has parts from both of these. So this is an example of exchange reaction. Okay. Okay. Now the compounds. In our body, we have both organic and inorganic compounds. So our body consists of both organic and inorganic compounds. Inorganic compounds, most common one is the water. Water is an inorganic compound and the most common inorganic compound of our body. Others are salts, acids, bases. Those are inorganic compounds. For example, sodium chloride. We all know that sodium chloride is regular salt. Right? So this is an inorganic compound. Hydrochloric acid. Okay? Carbonic acid. These are acids. Okay? Water. All these are inorganic compounds. Okay? In inorganic compounds, you have carbon atom. So in organic compound, we see carbon atoms are present. Not only that, we see in organic compounds, carbon atoms form the main structure of the molecule. Like this, we see many carbon atoms get attached to each other by the covalent bonds. Okay, so organic compounds, often you see the chemical formula is like this: many carbons that forms the basic framework, and you have others like oxygen, hydrogen, all those chemicals, but mainly carbon.
All of them always have carbon?
All organic compounds must have carbon. Yes. Uh, so those are the organic compounds: carbohydrates, fats, proteins, and nucleic acids. And carbons are connected by covalent bonds. Those I showed you by one or two lines. Covalent bond. If you see why we use one or two or three lines in between the atoms, that indicates how many pairs of electrons are shared. For example, if in this covalent bond you have two pairs of electrons are being shared, we will use two lines. If only one pair, we'll use one. So these lines actually indicate how many pairs are being shared by the atoms. Water is the most abundant inorganic compound in our body. 60 to 80% of volume of living cell is water. In early stage of life, the volume of water in a cell is more, but when you get old, body shrinks. You know that, right? Body shrinks. So the amount of water goes to the lower side. But still, the water is the main component of the body, human body or living cell. Water has some important properties. Those are very important for our life. High heat capacity. Water can hold a large amount of heat in it. Water can hold large amount of heat. So the water doesn't get cold or hot easily, because to make the water hot you have to add lot of heat, large amount of heat, right? To make it cold you have to remove lot of heat from it, so it will not easily get cold or hot, which is very good because our body is mainly what? Water, right? So if water gets cold very fast, when you go outside in cold weather, your body temperature will suddenly drop. Make sense? If water gets cold quickly, but that doesn't happen, which is good, right? If water gets very hot suddenly, when you go to a hot room or like Las Vegas, 110 degree, your body will suddenly become 110, right? If water turns hot very quickly, and you will die. If your body temperature is 110, you know that, right? So the high heat capacity of water is very good for our body, right? Survival. Water body will not turn cold or hot quickly. You can simply tell that water has high heat capacity. When you boil water, right? You put water in a pan and put on the stove. It takes long time, right? Slowly water gets hot because water takes a lot of heat inside. Then it turns hot, right? At the same time, when you pour the water in a cup, you make coffee, you can drink for a long time, hot coffee, right? It will not get quickly cold. That tells you that water takes a lot of heat inside it and will hold it for a long time, will not get cold quickly. High heat of vaporization. Water will not turn to air quickly. It needs a lot of heat to turn it to vapor, which is good. Also, just think that if your body water turns to vapor quickly, then what will happen? You will shrink, right? Water will leave the body and will quickly shrink. That doesn't happen, right? So water will not turn, your body water will not turn to vapor easily. Water is the major transport medium because the water in your blood transports many chemicals from one place to another place. Water is the site for many chemical reactions. I have mentioned thousands of chemical reactions are being continuously taken place in your body. Most of those chemical reactions occur in presence of water, in water. Without water, if the chemicals are dry, they will not produce reaction. So, for chemical reactions, you must dissolve the chemicals in water. If you have chemistry background, you know that. If you dissolve two chemicals in water and then mix, chemical reaction will occur, right? If you put them dry and put them together, keep them dry and put them together, usually chemical reaction will not occur, right? So your body water helps in chemical reactions. Cushioning. Cushioning is another important function of water. Uh, you know, let me give you a very simple example. Around your brain, you have cerebrospinal fluid. Around the brain, you have CSF, cerebrospinal fluid. That fluid provides cushion. And when you move your head suddenly, sometimes you go to roller coaster, right? You know that how quickly it moves. So if you didn't have that cerebrospinal fluid, your brain would have hit the hard skull bone and the brain damage would have occurred. That doesn't happen because around the brain you have the water fluid, cerebrospinal fluid. Okay, so another good example, in your tissue you have cells, many cells joined together to form the tissue, but in between the cells we have the water or interstitial fluid, mainly water. So that provides cushion, okay, between the cells. Acids and bases are also inorganic compounds, most of the acids and bases. So I will just briefly talk about acids and bases because chemistry class uh, will learn a lot more. This is physiology anatomy. So just I'll give you brief idea. Acids are hydrogen ion donors. Very simple. Hydrogen ion donors. And bases are hydrogen ion acceptors. Okay. So any chemical that can quickly donate hydrogen ions that are considered as acids. For example, hydrochloric acid, carbonic acid. Why these are acids? Because they can quickly release the hydrogen from them. Quickly release the hydrogen. Why sodium hydroxide is not an acid? Because it cannot quickly release hydrogen. It will not happen. It will not happen. Okay. So it is not an acid. When the hydrogen ion concentration increases in your body, hydrogen ion concentration increases in your body becomes acidic. So in any solution, when the hydrogen ion concentration increases, it becomes acidic. Make sense? So if in your body hydrogen ion production increases, your body will become acidic. That is called acidosis. Okay. Bases are hydrogen ion acceptors. Okay. So what happens? One common base is sodium hydroxide. Okay. So when acids and bases they come close to each other, sodium hydroxide and for example hydrochloric acid. So this hydrogen, we know that hydrochloric acid quickly releases hydrogen. Okay. So hydrogen is quickly released from the acid. We know that. Now when the base, this is a common base, will come close to hydrochloric acid, what will happen? The base will split into sodium and hydroxide. And what will happen then? This hydrogen ion and this OH, you see this is plus, this is minus, right? They will join together because one is positive, one is negative to produce what? H2O. Two hydrogen, one oxygen. Is it clear? To produce what? Water, right? And water is neutral. We know that water is neutral. So you see that base, how a base quickly removes the hydrogen ion from a solution. Make sense? Base will produce OH quickly produce OH, and that OH will quickly remove this free hydrogen ion and produce water. Make sense? So it will no more acidic because we know that if in a solution or body you have more hydrogen, that makes acidic. So if I add a base there, it will remove the hydrogen ion by producing OH and will make water. Water is neutral, no harm. Okay, so that's how a base removes the hydrogen ion by accepting the hydrogen ion. Okay, that's the acid and base. Strong acid, for example, HCl and H2CO3. If this one both release hydrogen ion quickly, but if this one releases hydrogen ion in less amount than this one in 1 unit of time, for example in 1 second, this one has released less hydrogen ion than this one, then this is stronger acid. So which one can produce the hydrogen ion faster? That is the stronger acid. But both must be able to quickly produce hydrogen ion.
Is that a timed thing? Because the amount of how quickly they go around in the bigger atoms, or no? What makes it faster or slower?
That depends. Chemical reaction depends on the temperature and many other factors, solubility, those things that I mentioned. Okay, most of the chemical reactions in our body occurs in normal body temperature, and if hypothermia occurs, the body temperature drops, chemical reactions get slow or even stop. Okay, in that case, the chemicals will not be produced. That's why hypothermia or hyperthermia both are dangerous because the chemical reactions will get slow. or will even may stop. That can stop the functions of the systems in your body. Now, the neutral pH is 7. 7.0 is neutral. For example, water. If the pH is above 7, it is alkaline. I think I mentioned this in last class. pH less than 7.0, that is acidic. Okay? Now there is a formula you already know by now. More hydrogen ion means more what? Acidic, right? Adding hydrogen ion will make it acidic. That means what? More or less pH. Less, right? If you go further down, more acidic. Okay? So pH, as pH goes down, it becomes stronger and stronger acidic. Make sense? So, for example, this one's pH is 6 here. That is acidic because below 7, 5. This is more acidic. If you go above 7, as you go up, it becomes more and more alkaline. Okay? Now you can say that more acidic means less pH. So that is the relationship. Okay, you need to remember this relationship. This is very important. More hydrogen ion. If I add hydrogen ion in your body fluid, your pH will go down. Makes sense? Will become acidic. So that you need to know. Here you see some household materials or food stock, their pH, and neutral is water 7. As you go down, becomes stronger acidic. As you go up, becomes stronger alkaline. Okay, now we have learned about acids and bases. Now we'll see the organic compounds. We have talked about water, acids, bases. Those are what? Inorganic compounds, right? That's why we have talked about those things. Those are inorganic compounds in your body. Now we'll see the organic compounds in your body. We are talking about body. Carbohydrates, fats, proteins, and nucleic acids. These are organic. Just briefly, we'll go over those. If you see the chemical formula of a carbohydrate molecule, it has carbon, hydrogen, oxygen, CHO. We classify carbohydrates into 3 types: monosaccharides, disaccharides, and polysaccharides. Monosaccharides are simple carbohydrates, very simple, small and simple. I have already mentioned, good example is glucose, right? Glucose is the simple sugar or carbohydrate. Okay. Disaccharides are double sugar. 2 monosaccharides joined together by dehydration reactions. You don't need to know that, just know that monosaccharides join together to form disaccharides. 2 monosaccharides, di means 2, join together to form disaccharide. Example, maltose, lactose, galactose, those are disaccharides. Polysaccharides. Polysaccharides have more than two mono or disaccharides. More than two. So disaccharides can join together or many monosaccharides can join together. Same thing to form polysaccharides. Largest and most complex carbohydrate molecules. Example, glycogen. I have already mentioned. I showed you in synthesis reaction, glucose join together to form glycogen, right? And that is stored in your body. So, glycogen. Another example, starch. So, those are polysaccharides, most complex carbohydrate forms. They are usually stored. Lipids. If you see a lipid molecule, you will either find CHO and or CHO and P. So, if CHO and P is present, phosphorus, that must be a fat or lipid. But if CHO are present, that is either carbohydrate or fat. But if P is present, that must be a lipid. Lipids are insoluble in water. We know that. Lipids, main lipids in our body are triglycerides. Those are also known as neutral fats. TG, triglycerides or neutral fats. Phospholipids and steroid. Another way we classify the lipids by looking at the fatty acids, the nature of fatty acids in that fat. We divide the lipids or fats into two types, saturated fat or fatty acids, unsaturated fat or fatty acids. If you see the chemical structure of a saturated fatty acid or fats, you will see plenty of hydrogen, H, and that's why it is called saturated. That means it is saturated by hydrogen. Lot of hydrogen is there. Why another type is called unsaturated? Because it has less amount of hydrogen. It is not saturated by hydrogen. Okay, so saturated has plenty of hydrogen, unsaturated has less amount of hydrogen, reduced number of hydrogen. In saturated fatty acid, you will see the carbon atoms are often connected by single bond. That means one pair of electrons, right? You know that. In unsaturated, you will often see double bonds. So, other differences between saturated and unsaturated, one is saturated fatty acids usually come from animal sources. Unsaturated fatty acids usually come from plant sources, from plants. Saturated fatty acids are found in solid form in normal room temperature. For example, cheese or butter, right? Those are in solid form in normal temperature. So those are saturated fatty acids. Make sense? Unsaturated usually found in liquid form. Saturated fatty acids are harmful for the health. Unsaturated fatty acids are not so. Why saturated fatty acids could be harmful? They love to block the arteries, right? And that could be dangerous. If in your heart the coronary artery is blocked, in your brain, the artery is blocked, then what will happen? You know, right? It could be dangerous. You may even die if that happens, right? So the saturated fatty acids love to accumulate inside the artery. Unsaturated or not. Saturated fatty acids. So who is your friend? Unsaturated. Saturated are not your friend, right? Could be your friend because saturated fatty acids are yummy, delicious, very tasty. You know, the butter or cheese, very delicious, right? You love to eat. So short-term friend, right? Like when you're eating, if I give you saturated and unsaturated, you would love to eat the saturated, right? Cake or cheese, but not for a long time. Eventually, it may kill you, right? Good friend will not kill you. Okay, so those are some differences between saturated and unsaturated fatty acids. Okay? Proteins. If you see a protein molecule, you will definitely find nitrogen and others are present, CHO, but also nitrogen must be present. Proteins are formed by amino acids. I mentioned a few minutes ago. Amino acids are connected by peptide bonds. You'll find in your note. That is the protein. So this is a protein molecule. Okay, protein molecule, and these are amino acid molecules. They join by peptide bonds. Now, amino acid. Each amino acid. If I break this one and see the chemical structure of an amino acid, it has amine, NH2 or 3, and carboxyl. So amino group, and this is COOH is carboxyl group. Okay, so these two groups are present in amino acid. Just know that in human body we need 20 different types of amino acids. Because 10 amino acids your body can produce. Okay, so those are the non-essential amino acids. Other 10 you have to directly get from the food. So those are called the essential amino acids because your body cannot produce. You have to take from, essentially you have to take from outside. So those are essential. You need to just know those. Energy. Energy in our body comes from ATP. I mentioned it before. The simplest way to formulate is, you get from outside nutrients, oxygen. These things we get from outside, right? Nutrients come from food, oxygen we take, and metabolism occurs inside the body. Metabolism occurs inside the body to produce what? Produce ATP, most important, energy. Okay. We also get water, heat. Those are produced by metabolism of nutrients and oxygen. Okay, ATP, water, heat. Also, waste. That means carbon dioxide, urea, uric acid. We have talked about it. So these are metabolic waste. Okay, these are good. These are bad. Should be excreted. Should be used in our body. We need ATP for many cellular processes. To open the ion channels, you see the top one. To cause the contraction of the muscle fibers, see the middle one. And for chemical reactions, to bring the molecules together. Many physiological processes require ATP or energy. Okay, so that's why we need ATP. Okay, that good? Lot of information. Okay.